So yeah, thanks very much for the invitation. I really like being back here. And thanks to all the master students that are present in the room. So listen, I tried to be, I was told to prepare something that was probably a little bit more informal. So interrupt me at any point if you have any questions, anything that is not clear, any complaints, or anything that you want. I mean, if you have a comment, that's also allowed. Okay, so just do anything that you want. The idea of this was also to complement a little bit what I think are the more experimental aspects that probably have been covered in the masters. Okay, so and because of that idea, I came up with this potential idea for the talk, which is to discuss a little bit how dark matter was originated in the universe. Okay. And different ways in which we can produce dark matter in the early universe, and what are the consequences for experiments today. That was the original idea. I'm not sure what I did in the end. Okay, so let's see where this takes us. Okay, so just to put things into a little bit of context. Okay, I think it's inevitable to start talking about dark matter by saying that we believe that dark matter is a necessary and also very important ingredient in our universe. It explains gravitational effects that we've seen at various in the universe and also at very different times. Okay, so I think you're probably familiar with this, but anyways, I think it's always nice to remember that we've seen the gravitational effects of dark matter at the scale of galaxies. For example, in spiral galaxies, just by seeing how the velocity of rotation of galaxies is different from what we expect from only luminous matter. We've also seen the effect of dark matter in bigger objects, okay, in clusters of galaxies, where we've also seen that the velocities of the objects which are inside the cluster are faster than they should be if there was only luminous matter. And also we've seen very interesting effects, for example, in dynamical objects, okay? So for example, collisions of clusters, okay? This is probably one of the best known images, which is the bullet cluster, in which we've seen how two clusters, after having collided, the dark matter and the visible matter get separated. And this actually also informs us about how strongly interacting is dark matter with itself, for example, okay? So because of this, we also know that dark matter not only interacts very weakly with standard model particles, but also very weakly with itself, okay? So this is also interesting to point out. And finally, we've also seen the imprint of dark matter in the first structures that we see in our universe. When our universe became transparent, we see the photons that were emitted back then. These also keep memory of what the components of the universe were. And by studying the anisotropies in the cosmic microwave background, we've come to essentially measure the abundance of dark matter, okay? Anyways, by studying the anisotropies in the CMB and fitting to all possible universes, we've come to realize that most of the universe is just made out of something obscure, in the sense of we don't know what it is. And there are mainly two obscure components that we call dark energy. Again, lacking a better name, dark energy is whatever makes the universe expand in an accelerated way. And that's, as far as I know, the best definition that I have for that. We also have a component which behaves as matter as the universe evolves. This is the equation. The pressure that it exerts, it is the same as if it was ordinary matter, okay? And that's what we call dark matter. And then the amount of ordinary matter that we know, or ordinary components in the universe that we know, is about 5%. Okay, so it's very humbling to realize that we only know about 5% of our universe. And then, of course, not only dark matter is present in these objects, which again, I would like to point out that they also correspond to different ages in the universe, okay? The CMB is back when the universe was 380,000 years old, okay? But also, and galaxies are today, okay? We've seen dark matter in the early universe, and we've seen it today. And dark matter is also fundamental to understand how the structures in the universe are formed, okay? So the filamentary structures that you should be... But anyways, I was just showing you here a numerical simulation in which corresponds to dark matter abundance or densities, and the overdensities are in clear color, okay? And it is luminous matter that follows these potential wells, and we end up with a network or a filamentary structure for the visible matter that we see in the universe. Matter is necessary. It makes the universe that we see. So the question is, of course, what is dark matter? Okay. We know that dark matter, at least this hypothesis that it's a particle, it's a massive particle, and it is neutral. Okay. Every time you see an asterisk here is that you can avoid that somehow under some conditions. Okay. There are milli charged particles, for example. Dark matter is stable. We've seen it in the early universe, and we see it today. So it has to at least have the lifetime of our universe. This means it can actually decay, but it has to do it on cosmological scales, and that's actually fine. We also know the cosmic abundance that we need to fulfill, which is the 27% of all the energy density of the universe that I showed before. And here, there's another word of caution, because for most of what I will be saying in this talk, I'm going to assume that dark matter is only made up of one single species. There's a priori no reason why that has to be the case, okay? We can also have multi-component dark matter. This is several particles of dark matter that make up the 27% at the end of the day, okay? And then obviously it has to be not excluded by current searches. And by current searches, we will probably talk a little bit more about this during the talk. But I mean searches in colliders, in experiments, in stars, everywhere, okay? Fortunately or unfortunately, depending on how you want to see this, there are many ways of fulfilling these conditions, okay? And in the last several decades, physicists have come up with very different ways in which dark matter can actually satisfy all the conditions that I showed before. This is a scale of interactions and a scale of masses. And if you look carefully, this is a kind of handwritten logarithmic scale, so it is not very precise. But anyway, there are about 60 orders of magnitude versus 60 orders of magnitude in each direction, okay? So action, for example, maybe we only need to add one particle to the standard model, together with the corresponding symmetries, etc. It is also very common that dark matter comes with some friends, okay? And in particular, for example, in the past decades, has also become very popular the idea of mediators. Dark matter lives in a hidden sector, and it talks to the standard model particles through the exchange of a new type of particle, okay? In the previous example, it was the Higgs, since we already know that the Higgs exists. I was putting it only as a... But maybe dark matter particle comes with other friends. This is very interesting, because it also offers the possibility of looking for dark matter indirectly through searches of the light mediator, for example. Okay, this can be done in colliders, etc., etc. This is a possibility that also fits very well with this more phenomenological idea of kind of simplified models as well. And then probably the extreme of this is when dark matter comes with a whole model behind, which is, for example, the case of supersymmetry, the case of other theories which are constructed from first principles, and in which dark matter, for example, is just a consequence of that theory. You know? In the case of supersymmetry, we not only have new mediators, but we also have a supersymmetric companion for each of the standard model particles. Okay. So again, by learning about dark matter, maybe we also learn, or I mean, necessarily we're going to learn about the physics, the nature of physics beyond the standard. Right. So just to also clarify how are we looking for dark matter, we have various ways to look for these exotic particles. Okay, we can look for them directly, and this is mainly trying to observe their scattering, absorption, or elastic or inelastic scattering, or whatever, inside experiments on Earth, which are typically underground. Okay. We can also look for dark matter particles in accelerators, in which case we will have to produce them in collisions of standard model particles. For example, if you're looking at the LHC, proton-proton collision, giving us jets, whatever, plus a standard model, plus a dark matter particle. There are astrophysical and cosmological proofs for dark matter, because dark matter can also affect the way in which objects, such as, for example, stars, behave. Stars can emit very light particles and free and cool down, for example, or be trapped gravitationally inside and annihilate inside the sun or other stars. So that's also something that we can look for. And this probably is also part of indirect searches in which we are looking for annihilation or decay of dark matter particles in the sky. In those positions of the universe where we think, for example, that there is an overabundance of dark matter, such as the galactic center. Okay? again, coming back to this idea of talking about particle physics, okay? I'm just gonna concentrate on which properties of particle models are constrained by these different types of observation, and I'm going to concentrate mostly on direct and indirect searches. In the case of direct detection, again, it is mostly looked for in underground experiments in which what you're looking for is the collision of a dark matter particle that traverses the crust of the Earth, reaches your experiment, just by chance collides with something there, and leaves some deposit of energy. The number of events that we expect in these kind of experiments is simply the integral of the scattering probability, the scattering cross-section, integrated for the possible velocities of dark matter inside your experimental setup. Okay, but all the particle physics content is included here, is encoded in the differential scattering cross-section. Okay, inevitably, we're also talking about what are the dark matter parameters in the halo. Okay, so you're also sensitive to how well do you know the halo of dark matter that we are living in. In particular, what is the local abundance of dark matter? What is the distribution of velocities of dark matter in our galaxy, etc. Okay, so it's subject to some uncertainties also here. And also, at least from the point of view of particle physics, it also incorporates effects of nuclear physics, material science, which are also very interesting. Okay, so I find that quite exciting. The cross-section can be very simple if you're talking about simplified models. It can be very complicated if you're talking about trying to include all the potential ways in which dark matter has to interact in your experiment. Okay, so it is up to you as a theorist to decide, for example, when you interpret experimental data, to interpret them into a more simplified parameter space or a wider parameter space. If you're only deriving constraints, this is more or less relevant, okay? But if you're trying to reconstruct dark matter particles once you have a positive detection, hopefully in the future, well, being aware of all the possibilities is actually necessary, okay? So I'm only including this. This is all the set of non-renormalizable, so all the set of non-relativistic operators that can mediate a dark matter nucleus interaction. Okay, so you can see that this is actually not as simple as just putting one parameter. Spoiler alert, okay, we haven't seen dark matter yet, or we don't think we have seen dark matter yet. Okay, and when you don't see it, what you do is you derive constraints, upper bounds, on the parameters of the model. Okay, and in this case, it is customary to interpret these upper bounds on the scattering cross-section, taking, for example, one projection in this wider parameter space that I was showing before. It is customary to take the spin-independent cross-section, which is this operator 1 here, just because it is also more, it's also simpler. And in terms of that, different experiments, by not finding dark matter, have ruled out regions of the parameter space with large scattering cross-section. Here I'm showing the results, for example, for novel liquid xenon experiments, such as LZ, xenon, etc., which have already ruled out the possibility of scattering cross-section above 10 to the minus 47 centimeters squared. And this is typically for masses around GeV scale or so. And further experiments are going to explore this parameter space a little bit more in the future. I will come back to this plot later on, okay? Here I only wanted to show that the future sensitivities of experiments are actually going to give us an increase of a couple of orders of magnitude in this simplified parameter space, okay? There are, in this case, to improve our experiments, there are two main avenues, which is making bigger experiments, which are more sensitive just because you have more material, or making experiments which are sensitive to lower values of the recoil energy, which helps you look for dark matter particles which are lighter. Okay, so these two strategies are pushing the limits to the left to lower dark matter masses, or down here below to smaller values of the cross-section. And that's how we're covering the parameter space. We hope to be covering the parameter space in the next decade. Okay. So complementary indirect searches are looking for annihilation decays of dark matter particles in the halo. You're actually not looking for the dark matter, you're looking for the products of this annihilation, which can be, in principle, they are standard model particles. So the tracers that you're looking for are gamma rays, antiparticles, and neutrinos. okay, because those are the ones for which we have experimental techniques to separate. And also, gamma rays are probably particularly interesting because the photons don't deviate, unlike, for example, antimatter, and they point towards the sources, and we have plenty of experiments or plenty of detectors which are looking for this kind of signatures. The gamma rays can be produced promptly, dark matter into photons, for example, although that's only a loop level process, so the scattering cross-section or the annihilation cross-section is going to be smaller. In any case, I wanted to point out that the observable here, when you relate it to particle physics, is the annihilation cross-section, is the probability of dark matter particles finding each other and annihilating to give you a pair of gamma rays or some photons as the final states of fragmentation, hadronization, etc. So this is if you ever have an observation in the detection, what you hope to reconstruct is the annihilation cross-section of these particles in the halo. Okay? Of course, it also comes, and again, I also wanted to point out, with some astrophysical input and so also some astrophysical uncertainties, mostly what is the distribution of dark matter along the line of sight where you're looking for, which is not particularly easy to recover because, again, we don't see dark matter. Okay? So just bear this in mind when you see all these plots, especially also remember that there are uncertainties or some subtleties that maybe we want to consider when dealing with the astrophysics. So this is the set of experimental constraints that we face, okay? So let's just take a step back now and talk again about particle physics, okay? Which is what we started talking about, okay? And in particular, how it is that dark matter was produced in the first place in the early universe, okay? And one hypothesis that has been probably worked to almost exhaustion already is the idea that dark matter particles were in thermal and chemical equilibrium in the early universe. This is, I have dark matter particles annihilating into standard model particles and the reverse process as well as dark matter scattering, for example, on standard model particles. Okay? And these processes in the early universe, if the temperature is high enough and the coupling of dark matter is not too small, they will be in equilibrium at a particular temperature. Okay, and this is interesting because it actually sets up the number abundance of dark matter particles at that particular time in the evolution of the universe. In particular, it is customary to represent the abundance of dark matter in terms of the yield. The yield is the number density divided by the entropy density, and we normally do this because the entropy density already encodes the evolution of the universe in terms of the volume. So, for example, if my universe obviously is expanding, if the number of dark matter particles doesn't change, the density of dark matter particles is going to decrease as the volume, but the yield is going to remain constant. Okay, it's going to factor in already that value, volume effect. And it is very easy, just simply using the condition of equilibrium to determine what is the number abundance of relativistic particles and non-relativistic particles in the early universe. Okay, this is a simple calculation that probably everybody has to do at least once in their lives, and it's just integrating the phase space distribution function at a given temperature. Okay, we are in the early universe, so we are also going to assume that the occupancy numbers are very small and the chemical potential is essentially zero. Okay, at least for what I'm going to be talking about. Here, probably the thing that we need to notice is that the yield for relativistic particles is independent of the volume, is essentially a constant. Independent of the temperature, is essentially a constant. It only depends on when your relativistic particles decouple. And this, for example, is the way that you will calculate the relic abundance of neutrinos. Okay, neutrinos are also a part of dark matter, almost by definition. Okay, we don't see the neutrinos. It's only that they are luckily, okay, there are not many of them. Well, there are plenty of them, but they are not very massive. So in terms of the relic density of neutrinos is very small. And for non-relativistic particles, which is what we're going to apply for dark matter, we obtain a factor, which is this one here, which is a Boltzmann suppression. Simply implies that when we have dark matter particles and the temperature of the universe decreases, if my dark matter particle was in equilibrium throughout the whole evolution, we wouldn't see anything today. Okay. Luckily, at some point, what happens is that as the universe is expanding, the annihilation of dark matter particles becomes less efficient, and at some point, the annihilation rate falls below the Hubble expansion rate. And when that happens, your dark matter particle chemically decouples, okay, and their number density is frozen. Why do I bring this here? Well, because again, the time in the universe at which this happened depends essentially on what is the microphysics that describes this annihilation. What is the particle physics model? Okay, and in particular, if my annihilation cross-section is larger, if my interaction of dark matter particles is larger, what happens is that the annihilation cross-section makes these particles stay in equilibrium for a bit longer, and the relative density decreases. Okay, so this is what we call thermal decoupling, if you want, okay, or the decoupling of what we call weakly interacting massive particles, or freeze out. Now, the main observation here is that the Planck data, or this 27% of dark matter that I mentioned before, allow us to determine essentially when the coupling had to happen. And this, again, related to microphysics, and we realize that, let me just take this here, and I'll go back there in a minute, that in order to reproduce the correct relative density, your dark matter particle has to have electroweak scale interactions. Okay, this is just a coincidence, and actually the level of that coincidence is actually quite tremendous, no? Because once you do essentially what you need to do is to solve Boltzmann equation in the early universe to encode all the interactions that you have here for dark matter particles into standard model into the corresponding conditional operator, okay, and simply solve the corresponding differential equation that you get. Okay, this is not particularly complicated. But in doing so, and you will realize here, okay, this is the common form of the Boltzmann equation, okay? On the left-hand side, you have the time evolution of the number density. You have a factor that encodes how the universe is expanding or how the universe is behaving, okay? This equation, normally, we give it for a Friedmann-Robertson-Lemaitre-Walker universe, okay? Normal expanding universe. But if you want to change, for example, something in the cosmic history of the universe, to include, for example, some clination or anything weird in the early universe, you would be modifying this term. The particle physics is all encoded here on the right-hand side, in the annihilation cross-section. All your processes, number-changing processes, elastic scattering, whatever, okay? It's all in there. And this is necessarily also going to include the corresponding couplings of dark matter, okay? Once you solve this, it is also customary to expand the annihilation cross-section into velocities. It's a kind of Taylor expansion into velocities, so that you have a velocity-independent term and higher order terms. This will become important a bit later when I compare to indirect detection searches, okay? And essentially, when you solve this differential equation, you end up with a relative density, which is inversely proportional to almost the annihilation cross-section, okay? Essentially, this is almost 1 over the annihilation cross-section. It's only that the different velocity terms scale up differently, okay? And in principle, notice here that once you put numbers, and in the top here you have the Planck mass, you have the speed of light, and you have the entropy density of the universe today. And these numbers somehow manage to give you something of the order of 10 to the minus 10 GeV minus 2, which is essentially typically the scale of electroweak interactions. Okay, so this is a tremendous coincidence. And this is very motivating because it says, okay, if I put electroweak scale interactions here, my annihilation cross-section is enough to give me omega h of the order of 0.1. And this is the reason behind what we call weakly interacting massive particles, okay? Why do we like these WIMPs? Well, also because they are very easy to look for. If my dark matter particle interacts only with electroweak scale interaction, then it's actually not impossible to see it in experiments, okay? Not only can I look for it in direct detection experiments, but also annihilation and even at colliders. And that's also one of the reasons why WIMPs became very, very popular. There's also a word of caution here, okay? When doing this parallelism, we are forgetting that there can also be some other effects. In particular, there can be annihilation effects. This is your dark matter particle, as I said before, may not come alone, okay? We may also have some other extra exotics in the bath in the early universe. If that happens, the presence of those particles also affects the time evolution of the number density of your dark matter. So actually, if dark matter annihilates in the presence of other exotics, that annihilation might even be more effective. Okay? There can also be effects of resonant annihilation, which is two dark matter particles having exactly one half of the mass of the particle that you're producing in such a way that you're producing it on shell. That gives you a resonance and then allows you to reconstruct the correct relic density for a smaller value of the coupling. So there's quite a lot of variation in the coupling. So when I'm saying electroweak scale, you have to take electroweak scale probably -3 orders of magnitude or even 4 orders of magnitude. Okay, so it can be a lot, especially in the case of resonant annihilation. Okay, and this again becomes very obvious when we look for these particles. So anyway, keep that in mind. Okay. Are we back? Yeah, very good. Right, so I didn't want to complicate this too much, okay? Again, the setup is that, or the argument that I want to make is that this is not a situation that is super weird, that never happens, okay? It is common that dark matter particles come with other exotics. And the full solution of the problem includes solving Boltzmann equation for your dark matter with the rest of the exotics as well, okay? Now, I'm simplifying it with only two, just to make an argument about when it is important to consider other particles. And to do that, let me compare the annihilation rate of this process, for example, which is chi1, chi1 into standard model particles, which would be proportional to the number density squared of particle 1 together with the corresponding annihilation cross-section. Let me take this other process, for example, which is chi2, chi2. Chi2 might be heavier than chi1, for example, with the corresponding annihilation. So when is important to consider this process if I want to calculate the relic density for chi1? Well, let's just take the fraction of those two rates. If the physics that is giving you the annihilation for this process is the same as this other process, we can assume, for example, that they are of the same order of magnitude, that there is not going to be a big difference in the annihilation cross-section. So let me just cross out these two factors here, and we only end up with the ratio of the number densities of these particles, okay? Remember that we're talking about non-relativistic candidates. These are massive particles, and so their number density is going to be proportional to that Boltzmann factor that I presented before, which is e to the minus the mass divided by the temperature. So this is going to be proportional to 1 divided by e minus the difference of masses divided by the temperature. The temperature at which these particles decouple is a fraction of their mass, which is about 1/20th of their mass. So when I put those numbers together, I end up with this exponential factor, which is, you see here, delta m, which is the difference of mass of the two objects divided by m. In order for this to be of order 1, I need that the difference of masses of particles 2 and 1 is at least smaller than or at least 5%. Which is good, okay? It tells you that you can ignore, when doing all this calculation, you can ignore any particle that is very heavy, because their number abundance is going to be very small in the universe when their particle is decoupling, okay? And it means that these co-annihilation effects only happen when the mass of the two exotic particles are very, very similar, okay? But anyway, that's important because it happens also more or less naturally in some of the models, okay? All right, so that's how we produce WIMPs, and again, some of the caveats in WIMP production that are probably open up the parameter space a little bit more. However, how do we determine whether we've seen a WIMP experimentally or not? Okay, it would seem that the crucial quantity to determine is the annihilation cross-section. This is, do I see a WIMP? Can I determine the annihilation cross-section, and does it coincide with the thermal value of 3 times 10 to the minus 26 centimeter cube per second that I mentioned before? And again, because of the experiments that I mentioned before, that I also mentioned in the beginning of my talk, it seems that indirect detection is probably the way to go, because indirect detection is giving us a measure of the annihilation cross-section. Okay, so let me go to the case of Fermi, okay, which is again one of the main gamma ray observatories at the moment. And this is the gamma ray sky as seen by Fermi. Okay, probably there is a newer plot, okay, but I didn't have the animation here, so I didn't use the newer plot. The thing with Fermi is that when you take out all the foreground emission, all the emission of gamma rays that we know it comes from astrophysical objects, and you reduce it, you end up with a signal that doesn't disappear in the galactic center. This is, you end up with photons that come from the galactic center for which you don't have in principle, an identified astrophysical origin. Okay, this is, you have a gamma ray excess, is what they call it, in the galactic center. Okay, what can this be? Well, because of the way that our galaxy and other galaxies are formed, okay, we expect that the dark matter density in the galactic center is larger than in the surrounding area. So this could actually be due to dark matter. Okay, can it be dark matter annihilated? Okay. And the answer is that in principle, yes.
So, sorry, David, what we were seeing, what it was fluctuating?
So what is fluctuating, sorry, is what I'm taking is the image before taking out the astrophysical background and the image that you get after taking the astrophysical background. And the different colors correspond to a larger number of photons. So what you're seeing here, and this is a zoom of this area here, what you're seeing here is that there are photons coming from the galactic center when you take out all the photons from non-astrophysical sources. Okay? This is probably the best way to see it anyways, this plot here, okay? Which in terms of the energy and the flux of photons, what you see is that you have something which is consistent or which is inconsistent with zero for a range of energies. Okay, and again, this is after subtracting all known astrophysical background. So this actually was quite interesting around 2010, 2015, because we were trying to understand whether this had an astrophysical origin or not. And people pointed out, for example, that there was a population of millisecond pulsars that could mimic this particular emission. So the issue is not yet completely clear. People are still working on this. However, what I find intriguing is that if you try to reconstruct this, assume that it is dark matter, what you find is different ways in which your dark matter can emit this signal. This is the annihilation cross-section as a function of the mass, and each of these circles corresponds to one possible dark matter solution when dark matter is annihilating into a single species. So, for example, from top to bottom, when dark matter annihilates into tau tau, it can produce the galactic gamma ray excess for a mass of about 10 GeV, and for an annihilation cross-section which is slightly below 10 to the minus 26. If you move up your annihilation into heavier particles, this moves up only a little bit. Okay, this is logarithmic scale, but notice that you're always around 10 to the minus 26 GeV, sorry, 10 to the minus 26 centimeter cube per second. Okay. So what is intriguing and what actually made a lot of us excited back then is that this actually corresponds to the value of your thermal annihilation cross-section. Okay, this looks like a win.
What about the angular extent of the block? Is also reproduced by the dark matter model?
That is one of the, the morphology of that is what they are, I think it fits better. I think the question was whether it fitted better the millisecond pulsars or dark matter, okay? I'm not sure at the moment, okay? There were arguments that I saw that the millisecond pulsars was a bit more contrived, but I don't know, yeah. It is not incompatible with dark matter. I think the main question here is whether it is compatible with millisecond pulsars. Yeah? For dark matter, it fits quite well. Yeah? So yeah, this is exciting, okay? And notice here that it tells you that dark matter could be in principle with a mass of 20 to 100 GeV and with an annihilation cross-section which seems thermal. Okay, so that's potentially good. However, results from other indirect detection experiments and also from Fermi Lab looking at other objects, in particular dwarf spheroidal galaxies, have produced no positive results. And this is one of the main problems in principle for this interpretation of dark matter. Okay? What you can see here in these two plots, what I've done is taking each of these blobs individually, or two of these blobs individually. Annihilation into BB bar, which is this the black one here, and annihilation into tau tau, I think. Okay, and these are the regions that are compatible with the galactic gamma ray excess in the center. Sorry, with the gamma ray excess in the galactic center, and the solid line corresponds to the Fermi Lab constraint using dwarf spheroidal galaxies. Dwarf spheroidal galaxies are objects which are believed to be dominated by dark matter, which are nearby the Earth, and in which the dark matter emission should, in principle, be also quite easy to observe, in principle. Okay, so they actually constitute one of the strongest constraints that we put on the annihilation cross-section. So again, in principle, this problem still exists. You also have to realize that when you're looking at dwarf spheroidal galaxies, you're sensitive to other other sources of astrophysical background or other sources of astrophysical uncertainties. In particular, how is dark matter distributed in dwarf spheroidal galaxies? What is the integral along the line of sight in these objects? Not only Fermi, but also AMS, Antares and IceCube also looking for neutrinos have also produced constraints. This is probably the map of constraints on the sigma V plane. The thermal annihilation cross-section is somewhere around here. Okay, this is Fermi again. So in principle, you can see that, well, okay,
from these other experiments, we only have constraints. Except possibly also from AMS, okay? And this is also a couple of years ago, looking for antiprotons in AMS also gave a little excess. And again, it's the same game, okay? You see an excess there, you try to find the model of dark matter that reconstructs that excess. This is the, again, in terms of the energy and the number of antiprotons that you see, you can see that there is a region in which it is incompatible in principle with zero. The problem with antimatter is that it is much more difficult to understand than simply gamma rays or neutrinos which travel on a straight line. Okay, with antimatter, you not only have the uncertainty in the source term, but also you have all the process of diffusion, convection, magnetic fields, etc., which affect the total flux of antimatter that you observe today. Anyway, if you interpret that only as an upper bound, what you find is that, again, this puts a constraint on the thermal cross-section, which is here represented by a red line. And this white or gray area here would correspond to that excess, if you want to interpret it as an excess. Okay? And again, the intriguing part is that this falls in exactly the same place as the Fermi lat excess in the galactic center. Okay? So there were some analysis, obviously, trying to do a combined analysis of both signals. And here I'm just leaving this here because it is, again, it's just motivating that if you have this potential combination of two experiments, that would allow you to potentially reconstruct the annihilation cross-section. Okay? The problem here is that, I mean, essentially, all the channels that were compatible with Fermi are compatible with AMS. So you don't get much more information other than potentially a confirmation of a signal. Okay. Anyways, this is still subject to uncertainties, to understanding whether the millisecond pulsars can still do the job, and to understand also all the processes of diffusion, convection, and magnetic fields, etc., that we have in AMS.
But where does this window of possible parameters fit in the exclusion plots of direct searches?
Yeah, that's a difficult question to answer, because I'm going to talk about direct searches now in a minute, and we can come back to that. But there are different diagrams. Okay. So if I'm talking about a simplified model, this is very easy. I only have a couple of parameters, and I can draw constraints there. But I can find many ways in which this is compatible with direct detection, simply because you're looking at different diagrams. Yes. So notice here that you're annihilating into gamma rays. Okay, which can come, I mean, normally they come just from, okay, let me give you a very easy example, okay? If I'm annihilating into BB bar, that is going to be correlated with the signal that you see in direct detection. Because you're going to have your annihilation into quarks, QQ bar if you want, okay? It's the same diagram that you're looking for, whatever comes in here. It's the same diagram that you're looking for directly when you're doing elastic scattering with a nucleus. Okay, because here eventually is the scattering cross-section with quarks. So that coupling is going to be correlated with that. But the solution, if I think, for example, that this comes from annihilation into tau tau, is completely free. Okay, or the correlation with WW is going to be different. So there are some diagrams that are correlated, and there are some diagrams like annihilation to WW that are not going to be correlated. Okay. Right. So probably also related to your question, no? Which is how does this constraint, which is also the question that you asked me, Marisa, no, when doing this talk. I'm finally coming to it. Okay. So which is how does this constraint win dark matter models, for example, no? And I mean, I don't have a collection of all the possible models, but I've selected one model that has many of the features that appears in normal dark matter models. It has co-annihilations, it has resonant annihilation, it has different channels for annihilation, etc., etc. All the well, the answer, first of all, is that malamente. Okay, almost missed that. And the reason for that is essentially here, what is in the blackboard, okay? That there are ways in which both signals are not correlated. this, in very small numbers, because there are many numbers, this is the annihilation cross-section as a function of the mass. These are two plots which correspond to the same model. The left plot, all the points in the left plot satisfy the relic abundance of dark matter. And all the points on the right plot correspond to subabundant, to underabundant dark matter. Okay, so just focus on the plot on the left-hand side. The thermal cross-section is essentially just here. And Fermi-Lab constraint is essentially this line. So you see that you have many possibilities still, which are thermally produced, which fall below actually your thermal cross-section of 3 times 10 to the minus 26 centimeters per centimeter per second. Some of this is because co-annihilation takes place, and this reduces this brings you down several orders of magnitude. Some others is because you have resonant annihilation, and many others is because the annihilation cross-section is velocity dependent. If it is velocity dependent, just remember that you cannot just say, okay, what I'm looking here is the annihilation cross-section, which is going to be the same as in my early universe. Because the velocity of that matter particle in the early universe was a small fraction of the velocity of light, but the velocity of that matter particles in your halo is 10 to the minus 3, 10 to the minus 4 times the velocity of light. So that means that your scattering cross-section is going to be v squared suppressed, which is a factor 10 to the minus 6, 10 to the minus 7. Okay? So, again, thermal production is a bit more subtle than just that line of 3 times 10 to the minus 56. Okay? So, yeah, there are many points which still satisfy all these constraints of thermal cross-section. Just for completeness, okay, Fermi is not only looking for a continuous or gamma rays. There's a very specialized search which looks for features, for example, monochromatic lines, or some signals that can come, for example, from probably the emission in final states of photons or something like that. Okay, so when you look at those, the constraints that they put are a little bit more correspond to smaller values of the cross section, but they're at the same time very sensitive to some particular ways of annihilating. And in particular, resonances can very quickly give you a signal above the background. Okay. But anyway, there is nothing at the moment. There are only constraints there. So okay, that is the situation with the annihilation cross section. So let's turn let's put the focus now on direct detection. I'm probably coming back to Carlos's question, okay, which is okay. If my indirect searches is not really constraining that much my dark matter models, how is direct detection doing so? Okay, it's another way of putting your question, probably. And the interesting thing is that, again, for a canonical WIMP, if we just do the WIMP argument and say my dark matter particle has electroweak scale interactions, many of the areas of the parameter space where dark matter would scatter off quarks are already excluded. Okay. In particular, for example, I can think of simplified models in which my dark matter annihilates into QQ bar, gets the relic density, and then I get my prediction for the scattering cross-section, and that falls about 10 to the minus 41 centimeters squared for masses of about 10 GeV or so. Okay, that was very interesting. I mean, the region of the parameter space, if you remember, was very interesting. A couple of well, I mean, it has been very interesting ever since, right? Because it fitted, or it was compatible with the Gamma Libra annual modulation. Okay, so it would have been also a very natural WIMP. Okay, for heavier WIMPs, you also fall around these areas. Okay, so unless you're invoking some co-annihilation or resonant annihilation or anything like that, your WIMP should have already been found. Okay. However, again, there are models, and this is again the same model as I was showing before, so this is probably more direct to your question, in which direct detection is really, the prediction for direct detection is really all over the place. Okay, and this is again, once you take into account that you can have annihilation in different channels which are correlated or not correlated, etc., etc. Okay, so all of this area of the parameter space above this line is excluded. You've got points essentially essentially all of it. Okay, so again, we are not really constraining everything yet. This is a supersymmetric example, for example. Okay, just to, I thought that Sven would be here, so I was trying to make Sven happy, but he's missing that. Okay? All right, so that is regarding WIMPs. Okay, and as you see, I was not very conclusive. But anyways, which other ways do we have to produce dark matter? Well, let's go back to our original hypothesis, which is that matter was in equilibrium in the early universe. What happens if I change that? What happens if my dark matter particle interacts more weakly than I thought it did? Well, in that case, maybe I can assume that my dark matter particle was never in thermal equilibrium. Okay, the universe never reheated up to a temperature that allowed my particle to be produced in thermal equilibrium. But still, it can be produced in out of equilibrium processes. For example, imagine that my dark matter particle can be produced in the decay of a heavy particle. I'm calling it B2 and B1 because these are particles which are in equilibrium in the bath, okay, in thermal bath, okay? If the coupling of dark matter here is very, very small, again, my dark matter particle essentially is not in equilibrium, but that doesn't matter. My particle B2 is going to be decaying continuously on my dark matter particle throughout the evolution of the universe, and this is going to build up a relic density of my dark matter particle, okay? Without it being in thermal equilibrium. It's never going to be in thermal equilibrium. How do we solve this? The solution is essentially we have to just go back to the Boltzmann equation, write the corresponding collisional operator, which is, this is the number changing process that we have now to take care of. And in this case, in this particular example, it's very simple, okay? Just to give you, I didn't spend too much time on the other one because I think everybody has seen WIMPs, but let me just explain here a little bit more what this is about. What I'm writing here in the collisional operator is the integral in the phase space of the three particles which are involved, obviously imposing momentum and energy conservation. And here I'm considering the two processes, okay? B2 annihilating into B1. And the probability of this process happening is going to be the corresponding matrix element squared, the phase space distribution function of the original particles, and the available phase space of the two target particles. Okay? Likewise, I also have to consider the inverse process in which my two particles coalesce to give me a B2. And that is just the corresponding matrix element as well. The phase space distribution function of my dark matter particle and B1, and the available phase space in B2. Now, if dark matter has never been in equilibrium, this second term is essentially zero. My dark matter is not present from the beginning. And then this calculation is just very simple. Notice here, this integral is just the matrix element of the decay process integrated in the phase space of the three particles. So it is a kind of thermalized decay rate, if you want. Okay? So the solution to this problem is actually very simple. The yield can be calculated essentially analytically, and contains also the same crazy factors as the thermal relic density for WIMPs, okay? The Planck mass, the entropy density, etc., etc. The only thing that happens now is that your particle is produced at a different time in the evolution. In particular, again, this is the yield as a function of time. What happens is that your dark matter particle, which in the beginning was essentially zero, just builds up and stabilizes. Essentially, it stabilizes at a temperature which is essentially a small fraction of the mass of B2. Okay, it's essentially a factor of 8. And once it stabilizes, it just remains like that. Okay, it's never been in equilibrium. Now, the main difference with WIMPs is the following: that the abundance of your dark matter particle is proportional to the coupling and not proportional to the inverse coupling. Okay, if I increase the coupling of dark matter, the only thing that I'm doing is I'm producing more dark matter because I'm making this decay process more likely. Okay, so it's the opposite dependence on the coupling as we have for WIMPs. And this is very interesting again because I can play the same game. I know where I want to be here because I've measured the abundance of dark matter today, and this tells me how strong dark matter has to be produced in the right amount. And if I do that, I end up with a very small coupling, okay? For example, for the process that I was showing before, which is just a decay, I end up with something of the order of 10 to the minus 13. Okay? So instead of it being electro-weakly interacting, it's super mega weakly interacting. Okay? This might be a problem for looking for dark matter, but in principle, it is also it fits also very naturally. If I increase this coupling, I increase the abundance. Okay? These two cases, I mean, this is what's called freeze-in of dark matter. Freeze-in and freeze-out, I mean, normally they're presented as if they were two different things, but it's essentially solving Boltzmann equation in two different regimes. If I continue increasing my coupling, what is going to happen is that at some point the coupling is going to be so large that dark matter particle is going to be back in thermal equilibrium. And then I'm back to the case of wind. Okay, so these lines would essentially go back to the thermal one and then they would stabilize. Okay? So the same model can behave as a freeze-in or freeze-out depending on what is the size of the coupling. There is no mystery. But the idea of this coupling is that it also can be related to problems or to models which have naturally very small scales. For example, if you include particles which only interact gravitationally. So again, coming back to supersymmetry, because you have models in which the gravitino, the supersymmetric companion of the graviton, was a dark matter candidate, and the type of interactions that it had was essentially almost of this order. So the gravitino is a candidate that can be produced thermally in freezing kind of interactions. Okay? Now the challenge is, how do you look for this? And the problem is that because the interaction scale is so small, looking for it directly or indirectly is a bit more challenging. However, for example, the annihilation with electrons, here I'm actually reducing the value of the mass of the dark matter a lot. Okay, this allows me to look for dark matter particles in the range of keV or MeV. Here's where I overcome a little bit this this very small coupling. Okay, and in particular, for example, there have been attempts to say, okay, maybe my dark matter can be produced from annihilation of electrons out of equilibrium, or even plasmon decays in the early universe. This is just the photon has an effective mass, it decays into two of these dark matter particles. Okay. And in that case, I mean, you can do the same exercise as I did before. It's just a little bit, you just calculate the yield as the annihilation cross-section. This is what comes out of the Boltzmann equation. And eventually it leads you to something which is almost of the same order, okay, 10 to the minus 12. 4 masses of the order of the MeV. Okay. And in this case, I can actually look for the elastic scattering of dark matter particles with electrons in direct dark matter experiments. Okay. Again, I get a preferred region of the parameter space. This is the scattering cross-section with electrons as a function of the mass. The experimental probes are a little bit higher than these theoretical predictions. Well, a little bit is a couple of orders of magnitude. Okay, this is a logarithmic plot. Actually, I'm quoting here one of the results from Damick, which is probably getting closer. Okay, this is 10 to the minus 35, and this is 10 to the minus 37. Okay, so this looks very small, but there's still one order of magnitude to go. Okay, but these are in principle models that could show up, why not, in direct detection, freezing dark matter through. As you can see here, okay, this can be generalized in different ways. Okay, what I'm doing here is I'm generalizing this idea of freezing. The previous case was assuming a massless mediator. In this case, we're assuming a massive one. The energy dependence is different, but again, the name of the game is essentially the same. Okay, you calculate the theoretical predictions, you see more or less whether or not your experiment is going to probe them, and ideally, in this case, what we will need to essentially certify that we are seeing a freezing dark matter candidate would be to be able to reconstruct that value of the coupling of 10 to the minus 12, 10 to the minus 11, depending on the production. Okay. In this case, again, as I think, direct detection would be probably one of the ways to go. Okay. Some of the lines that you see here, actually, the line for freezing with massive mediators would be this solid line here on the top. Some of the other lines that you see here correspond to other dark matter production mechanisms that I will not be able to talk about today. But ones that at least I will mention is the possibility that dark matter is produced through a process which is similar to the way that baryons are produced, okay? Which is an asymmetry in the evolution in the early universe, okay? What we call asymmetric dark matter, the relic abundance would be similar to the abundance of baryons, and the only difference, the only reason why dark matter particles would contribute more to the energy density of the universe is because they are slightly heavier than protons, for example, okay? Asymmetric dark matter would also be more or less here. So again, I mean, there are various ways, and this also goes back to the idea that maybe detecting one of these candidates allow us to differentiate some of the production mechanisms for dark matter. Okay? I only have 10 minutes left, okay, but I think it's I cannot come here and not mention actions, okay? So, but also, I mean, in terms of productions, actions are produced in a completely different way, okay? And we are talking about, again, observing actions would tell us that the way that the dark matter is produced is completely different to freeze in, freeze out, etc. Okay? Very quickly, okay, I'm not going to stop on the theory of actions much, okay, but actions were proposed to address the strong QCD problem. Essentially, why is there a potential term in your QCD Lagrangian that is in principle CP violating, okay, but it is experimentally very constrained by the neutron EDM. And the way that actions solve it is that you have a dynamical solution in which you introduce a complex field that develops a back-in expectation value, and the back-in expectation value is related to that scale, FA, the scale of the action, okay? The action mass is therefore related to a new scale. Just to give you some numbers here, if the scale of the action is of order 10 to the minus 11, 10 to the minus 12 GeV, sorry, 10 to the, probably there's a minus there that should be plus, right? For 10 to the 12 GeV, you get masses of the action of 10 to the minus 5 electron volts, okay? So that is the kind of masses that we're talking about. So the main question, if this is the first time that you encounter this problem or this solution, and you're only familiar with WIMPs, your main question is saying, okay, this dark matter particle is very light. That is going to be relativistic, and that is not a viable dark matter particle. No? But that is related to how actions are produced in the early universe, okay? And this is, again, related to the solution to the strong, to the CP problem, no? The strong CP problem. Let's consider, again, the evolution of the universe as the temperature decreases, okay? And we're going to go to a temperature which is sufficiently high, above a certain scale that we call the Pet-Sykes scale, in which there's a U1 symmetry that is still preserved. In that case, I'm representing here the potential for a complex field. The minimum is just at 0. The back-in expectation value is at 0, nothing happens. The moment I go below this scale, this potential develops a kind of sombrero behavior, in which I still have a remaining direction, which is this angular direction, which is still flat. So in principle, my complex field would choose one potential angle here. The radial distance would be fixed, and this is actually what is fixed in the strong QCD problem. And I will still have one remaining degree of freedom. Okay, that is what I'm calling the action, that angular. And the potential along that line is essentially flat. So whether I end up in one angle or another is completely stochastic. If I continue decreasing the temperature, at some point there are non-perturbative QCD effects that give my action a mass. And essentially what this does to this potential is it tilts it a little bit in such a way that not all of these points are already a minimum. The potential changes from being completely flat to developing a minimum, a particular value of the angle. What happens then is that your action that very happily froze out or chose a particular angle here suddenly finds itself displaced from the real minimum of the potential and crawls back to that minimum, okay? And this is we call this realignment or misalignment mechanism that I've seen with both names, Okay. In doing so, it transfers this energy density, or this energy density is actually related to the relative density of this particle in the early universe. Okay. You can do again the equation of motion for the action can be computed like that. Here it depends a little bit on whether your Quinn scale is above the reheating temperature of the universe or below. If we're assuming that it is Quinn scale is above, your universe after, let's say that after having chosen this value, okay, inflation would make sure that that value of the angle is preserved for the whole universe, okay, or at least the whole visible universe. So essentially, there is no special derivative with respect to the angle, and this equation can be simplified just to show some kind of damped harmonic oscillator, okay? And this is the key point here. When you estimate the momentum of the resulting quanta for the action, what you end up with is that the momentum is of order. Here I've done some quick estimates, okay, for action scale of 10 to the 12 GeV. You end up with a momentum of 10 to the minus 9 electron volts. So even if your action is very light, remember that the typical mass is going to be 10 to the minus 5 electron volts, your action is still going to be non-relativistic. Okay, so that's actually fine because we still want cold dark matter, and the action is going to be a candidate for that. The initial energy of the action before starting oscillating is related to the relative density, and in particular, I can write the relative density as a prefactor that contains the action scale, the mass of the action, and the displacement angle. And here is when I can use some naturalness arguments. Okay, if theta is of the order of 1, then that gives me a value for the action scale for which the action reproduces the correct relative density. And that is actually this value of about 10 to the 12 GeV or so, for which again the action has a mass of 10 to the minus 5 electron volts. So that is, again, another potential solution for the dark matter problem. That is very interesting because it solves another existing problem in particle physics, and that gives you a completely different production mechanism that you had before. Okay. You may be wondering, okay, of course, I mean, given that scale, some actions are still going to be produced. I mean, it's just talked about freezing a moment ago, okay? So even if they are not in thermal equilibrium because the scale is very small, actions can still be produced, or at least part of them can still be produced by a freezing mechanism. The problem with that is that those actions produced that way are going to be relativistic, so I don't want there to be many of them. So that actually sets up a value, an upper value on the actual mass, which I think is of the order of 0.5 electron volts. Anyway, the message is that, yes, there are going to be some actions produced thermally, but these are going to be in the solution, the region of the parameter space where we consider the action as solution for dark matter, these are going to be negligible. Okay? Probably just to finish, probably in time, the actions can be looked for, obviously. I mean, the way that they are produced is also related to the way that we are looking for them, okay? And actions can be produced, can be looked for because of their coupling to photons, okay? So there are processes that involve converting actions into photons or photons into actions, either to produce them or to detect them, which are relevant for their searches, okay? In particular, the coupling to photons in the Lagrangian is related to the production of actions in solar interiors, which can actually account for some potential cooling of some of these objects, for example, in white dwarfs. They can also be produced in the laboratory if you're shooting a laser in a magnetic field. They can be detected in a magnet, for example. If you're pointing your magnet to the sun, can be converted into a photon, which then you detect. Okay. There are some other potential couplings of actions to either nuclei or also electrons, which are potentially also interesting for their detection. In particular, the axioelectric effect implies, for example, that the action can be absorbed by electrons, and we can also look for them even in direct detection experiments. I mean, well, these are direct detection experiments, but even in experiments which are being designed for WIMPs, okay? So the actions are very versatile, and it's yet another part of the yeah, of the whole zoo of dark matter production that I wanted to talk about today. This is just a sum of the region in which the action is a viable dark matter candidate, okay, with masses about 10 to the minus 5 electron volts. Some theoretical preferred models are here, and these are the different searches that are already constraining that parameter space quite a lot. Okay. A wider picture shows you that this was assumed about here. There are ways in which some specific searches are looking for particles which have the same properties as actions, but they just don't have the relation between the mass and the coupling that is predicted by some QCD models. Okay, and those are the so-called action-like particles. Okay, the search for these particles is essentially the same, but just in different regions of the parameter space. Okay, and this is probably, if you want to see these limits are from Kieran O'Hare. Just visit the webpage, and I think this is a very good map of the experimental situation nowadays. So I think I'm gonna finish probably here and leave some time for questions or some discussion if you want. Okay. So just to conclude, I think I tried to make the argument that the dark matter problem is intimately related to cosmology. How is the cosmology of the early universe? Dark matter can be produced in a variety of ways, which seem to point towards either perhaps a misleading coincidence or something more profound with some of the parameters which are involved. I've talked a little bit about WIMPs, in which that coincidence was due to the electroweak scale and it appearing almost magically from the freeze out of dark matter particles. In the case of freezing, you've seen that the same relative density could be obtained by a much smaller value of the coupling, but still could be interesting for decaying dark matter or gravitational interacting dark matter. And finally, I mentioned the case of actions, which are also linked to the resolution of a fundamental problem in QCD. Something that I have avoided, although I've used the word a couple of times, is natural. Many of these problems are actually related to naturalness issues of the standard model or extensions of the standard model. I've tried to avoid using that because I don't know exactly where my position is at the moment with that. Okay, supersymmetry was a potential solution for that, but we haven't seen it yet. But I think it's worth mentioning that having some theoretical guidance on whether you have a more fundamental scale that also is useful for dark matter is kind of interesting. Okay. In any case, talking about naturalness is always tricky. Okay, because that always reminds me of some things that don't, or some animals that are not very natural, or they are. But let me finish here. Okay, and maybe we have time for discussion or questions or anything. Yeah. Thank you.